Buenas noches. Si gustan ocupar sus lugares para dar inicio. Muchas gracias por estar aquí con nosotros en otra sesión de Gigantes de la Medicina. En nombre de Salud del Tecnológico de Monterrey, les agradecemos su presencia y esperamos que disfruten de esta sesión que abre el nuevo inicio de cursos de la Escuela de Medicina y Ciencias de la Salud. Le voy a ceder el micrófono al doctor Manuel Pérez Jiménez, decano de la Escuela de Medicina y Ciencias de la Salud, Región Norte, para que nos presente a nuestro invitado especial.
Buenas noches a todos y muchas gracias por estar aquí con nosotros. Realmente esta sesión se ha vuelto ya una muy buena costumbre, una sesión académica que va tomando un posicionamiento dentro de nuestra institución, y hoy tenemos el placer de que nos acompañe el doctor Arnold Caplan, al cual les presentaré en breve. Primero quiero agradecerle al doctor Barrera todo el esfuerzo y la invitación, porque gracias a él el doctor Caplan está con nosotros, y en respeto al doctor Caplan haré la presentación, una muy breve presentación, realmente es una reseña muy sencilla en inglés para que él nos entienda. Dr. Caplan, very welcome to Monterrey, at the Tech of Monterrey, and thank you for being here with us. Dr. Caplan is a professor of biology and director of the Skeletal Research Center at Case Western Reserve University. He received his PhD from the Johns Hopkins University School of Medicine. Dr. Caplan is a national and international scholar focusing on experimentation in the area of musculoskeletal and skin development. He has published over 400 papers and manuscripts and has long been supported by the NIH and other nonprofit and for-profit agencies for these efforts in trying to understand the development, maturation, and aging of cartilage, bone, skin, and other mesenchymal tissues, and for his pioneering research on mesenchymal stem cells. Dr. Caplan, welcome again, and please join us here on the stage. And also I'm going to but to ask Dr. Guillermo Torre, our president of Salud, to start the session. Thank you very much, and welcome for everyone.
Gracias, Manuel. Dr. Caplan, thank you for being here. I think I'm not going to repeat on Manuel's introduction, but I want you to know that this is a very important meeting tonight, because in the past we had predominantly physicians and not scientists, and we have made a big commitment in the university and in the medical school to try to push science at a more relevant level for the university and also in the medical school. In fact, your good friend Hugo is a symbol of that. We spend a lot of time discussing and talking, so we convinced him to come and work and help us develop that agenda. So I very much welcome and appreciate your presence here, because it's in some ways a symbol of what we want to continue to do, a commitment to advance and push science locally and hopefully with an impact eventually in a field somewhere internationally. But so with this idea in mind, I'll just repeat for everybody, these are informal conversations where we try to highlight some aspects of someone who's very prominent, accomplished, and share in this case, his experience and his career development and why choosing the field of expertise that he has today. So, Dr. Caplan, why don't we start just by you sharing with us your background? Where were you born? Although you and I had a brief conversation now, but what was your family environment, and maybe what pushed you to go into science, and then we can talk a little more about your career.
So, first of all, my apologies for not speaking Spanish. It's in my neighborhood that I grew up in Chicago, English was a big problem. So I have trouble also with English. So my mother and father were never graduated from high school. So my father never graduated from grammar school. He had to work. It was a different time. So by the time I graduated high school, I was completely out of the experience range of my parents. So I was very much an individual. I was very much had to make my own decisions, except my father was 5'6", and his arms were as thick as my thighs. He was a very strong street person, and he drove a truck in Chicago to deliver newspapers. And on Saturday, when I was 8 years old, I went to work. I started to work on my father's truck for $2 a day plus lunch. And I put the Sunday comics inside the Sunday paper, which in Chicago went on sale at noon on Saturday.
There was the Chicago Tribune?
There was the Chicago Tribune, no doubt. And of course, you idolize your father, right? And he's this big guy, and he's on a big truck. And every time I got on the truck after him, he put his finger out and he said, "You will not be a truck driver. You will go to college, or I will break every bone in your body." So obviously I became very interested in orthopedics. So it turns out that we were very poor and very unsophisticated. We were real city peasants. And I did things in Chicago which the president wouldn't believe, because he was at the University of Chicago. But I was a hoodlum in the middle of the city, because when you're poor, you only think about survival. You don't think about sophisticated questions. And going to school was obligatory, otherwise my father would break every bone in my body. And so I did okay in school. I wasn't all A's, but I did okay. And when I was in high school, I registered at the University of Illinois campus in Chicago, because it was the cheapest place to get an education. And I met the valedictorian of our graduating class from high school in the hall, and I said, "Where are you going to college?" And he said, "I'm going to IIT. I said, "What's that?" He said, "Illinois Institute of Technology. It's an engineering school." I said, "Oh, what are you going to be?" He said, "I'm going to be a chemical engineer." And I said, "What is that?" And he said, "That's a guy who works for petroleum companies, making sure you can take petroleum and make it into gas." So I figured, this guy's the smartest guy in class. I should go to that university. So from working, I had a total of $600 in my savings account. It's all the money I had in the world. That was the first year's full tuition. So I went to Illinois Institute of Technology as a chemical engineer. And in my junior year, I decided I couldn't be an engineer, and I decided that I would go to medical school or to graduate school. But I couldn't decide which, whether to be a researcher or an MD. So I was accepted to 4 places for graduate school. One was University of Chicago, an MD PhD program. They were offering me a lot of money, actually. So for a poor kid from Chicago, it was very tantalizing. I applied to Berkeley in California. It's a very good thing I didn't go to Berkeley, because I would have been a hippie.
Yeah, that was in the late 60s or 70s, or?
No, it's worse. It's it's 1963.
60, okay.
Okay, so it's when the hippies were still fashionable, and were exploding in San Francisco was the hippie center of the universe.
It remains probably.
And it remains that, and Berkeley was the starting place of all of this. And of course, why wouldn't I do that? So, because I was so you have to understand, you're all enormously sophisticated. You're in medical school. So you've gone through high school, you have this college experience, and you're on your way in a professional activity. You can't decide whether you want to be a cardiologist or whatever, but you're in this program. So you're a million times more sophisticated than I was. And so University of Chicago, Berkeley, I applied to Johns Hopkins because I had a cousin, a female cousin, who was exactly my age, and I knew if I went to Baltimore, where Johns Hopkins was, she could fix me up with a date with nice women. So that's called a hormonal decision. And then the other place was the University of Wisconsin, which was at that time inventing vitamin D. And as a biochemist, I was very interested in this whole area. But I went there and I found the faculty to be not so nice and not very responsive to young people. So that was out. Berkeley was too far. University of Chicago, I went and interviewed in the program, but I instinctively knew I had to leave Chicago to grow up. And so I went to Johns Hopkins and took the first 2 years of medical school. And at Hopkins, like here, everybody got a white coat with our names on the white coat, right? It was real wonderful for our egos, right? With Dr. Caplan on the lapel, and we all had to wear white shirts and ties, and I would go play doctor. And so I would take classes, but I would go to the emergency room, so I helped suture people. I delivered babies by myself. If a cab driver can deliver a baby, why can't I? And so I was looking at the hospital for professional reasons and trying to understand all the different areas. And one of my friends was in pediatrics. And he was already a physician, and I met him one morning in his clinic. And the clinic had these wooden benches and then a hallway with flags outside the examining room so you knew which doctor was where. And so I was late. I saw his flag, went into this room, and he said, "Oh, Arnold, I'm really glad, Dr. Caplan, I'm glad to see you. Would you hand me those calipers?" So they're measuring devices for skull size. And I went and handed him the calipers, and he said, "Would you please record these numbers in the patient's, in this young baby's history?" And I saw that this baby was going to die of hydrocephalus, of just his head was blowing up. And I got so upset that I thought I was going to pass out. And I politely excused myself and went into the clinic area and put my head between my knees because I was this close from fainting. And in those days, the disinfectant was wintergreen, this overpowering smell of wintergreen in my face, and I finally controlled myself. And at that moment, I decided that I didn't want to lose the ability to cry. Took my name tag off, threw it in the garbage can, and became a scientist. And so I did my PhD, and actually I'm going to show just some I know I should be talking. I want to show a few slides.
No, this is easy for me. I don't have to ask you any questions.
So I'm going to...
No.
I can't change the slide.
But I think while you get the slides, I think I don't know that I want to emphasize and make sure that people understand the decision that he was making, that he was in med school, and then because of that experience and maybe a desire that you'll talk to us more a little bit later, that conversion from going to medicine to science. Were you exposed to people in science that helped you make that decision, or what exactly, other than that experience where you felt?
No, I was already accepted to graduate school. Mm-hmm. So instead of taking courses for graduate school, I took first 2 years of medical school.
Okay.
So instead of taking a chemistry, I took gross anatomy instead of etc. So for my course credit, I took
medical school courses.
I took all of the medical school courses. Yeah. So this is my CV. I'm gonna stand up because I'm too old to see this on the side. So this is the next slide. So these are, no, somebody's going too fast. So go back. So this was, you can see me, what a absolutely adorable child I was. 3 years old. This is what my parents dressed me in. Next slide. And this is Albert Leninger. This was the guy. Leninger. Biochemist. And you can see in this corner is the textbook he wrote, which made him famous. He wrote a textbook in biochemistry. He had to memorize all the pathways.
So do I, yeah. We had that textbook. Yeah.
Right. And Leninger worked on mitochondria, which is a picture on the right side. And my thesis was to separate the inner and outer membrane of mitochondria and showed that electron transport was on the inner membrane. So this was at the forefront of biochemistry in those days. And this was, Leninger was the youngest department chairman in the history of the medical school. And so he was called Young Al Leninger, very formal, very New England kind of guy, very interesting guy. Taught me a very important lesson, which is our job is to discover new things. But our major job is to communicate them, both in writing and verbally. Because if you do the most brilliant experiment, but nobody knows about it, it doesn't exist. So our job is communicators. So he's a giant on whose shoulders I grew. Next slide. This is Ernesto Carafoli, was the postdoc in Leninger's lab, who taught me how to do real science, bench science. Carafoli's a world's expert on calcium channel movements. And underneath Leninger is Peter Mitchell. Mitchell had a theory about how energy worked in mitochondria. It's called a chemiosmotic hypothesis, for which Leninger and Britton Chance, who's on the bottom of that, who was at the University of Pennsylvania and actually got a gold medal as an Olympic sailor before he became a great scientist. Leninger and Ephraim Racker, who's the gentleman on the far left, all had a chemical hypothesis for how ATP is formed. They were completely wrong, not a little bit, but completely, and fought Mitchell for many years. And Mitchell's hypothesis not only turned out to be correct, but he received the Nobel Prize for that. And that's, again, one of the lessons I learned, which is you want to do science at the highest quality, and if you get a Nobel Prize, couldn't be anything better, because it means you're recognized all over the world for a few experiments that you do. So next slide. So the man on the left is Edgar Zwilling, and the man on the right is Nathan O. Caplan. Caplan was a great biochemist and a communicator, invented methods of enzymology, the books that we all learned biochemistry from. And Ed Zwilling was a developmental biologist who taught me all the embryology I know. I would go into his office and say, Ed, how does the kidney form? And then 2 hours later, I would know how the kidney forms. He would tell me the details. And so both of these gentlemen were giants as scientists and as educators. Next slide. So this is what I did and this is the last slide. This is what I did in Zwilling's lab. I invented a way of taking an embryonic chick limb bud, cutting it off the embryo, taking the mesenchymal cells and putting them in tissue culture and watching them differentiate into muscle, cartilage, and bone. And so this is what I worked on when I went to Case Western Reserve, and this is what gave me the experience to go into mesenchymal stem cells, because I was working with embryonic cells. But those men who were giants, real giants, not a small person like me, real giant, these are the people who taught me how to do science and taught me how to love what I did. And Leninger in particular taught me the art of communication, because the first research report I wrote, I came into his office. He destroyed it. He destroyed me because he said, all of the experiments, Arnold, are perfect. This is a perfect publications. All the figures are perfect. Your ability to communicate is marginal. And then I got lecture 101, which is your job is not only to do good science, but if you don't communicate it, it doesn't exist. And so thank you, that's all the slides. No, well, this is one last side of Hugo, with the other giant that influenced both Hugo and myself is Pierre Chambon, who's a fabulous molecular biologist who should have won a Nobel Prize, but for political reasons didn't. But both Hugo and I were hugely influenced by the organizational capacity and genius of Pierre Chambon. And the lesson that Pierre Chambon taught both of us is, no matter who else is doing the same experiment, he could do it better. He could do it better. And although that's a French chauvinistic attitude, he did do it better in lots of ways and brought the level of science in molecular biology to new levels, and was a fabulous organizer of scientists. Thank you, that's all the slides.
So let me maybe make you spend a couple more minutes again in these in the idea of science and medicine, because it's become clear that at least academic careers, whether it's in Europe or the US or in Mexico, it's very hard to be able to do both. And years ago here, we created a Mexican program of a combined MD-PhD program. Because the way the legislature or the requirements for medical school were complicated to allow a combined program. But we did that, and there are at least, I think, at least one more program in the country doing a combined program, not people that do an MD and then PhD, or they go PhD into an MD. So if you we're back with what you know today, and you were making the decision today, like we have people here that are in med school that may have the opportunity to go into a science career, what type of advice would you give to students that are not yet, or that are in the process of defining their career but not graduated from med school, as to how to pursue or how to see science as an alternative for a career? Is something that comes naturally, that either you're born with that desire, or is something acquired, or what is it that causes, you think, the greatest influence to try to make a decision to pursue a science career, whether it is a straight PhD or an MD PhD program?
That's a very hard question. I think there was a very good friend of mine who's a plastic surgeon who quit plastic surgery to become an entrepreneur, to start a business in regenerative medicine. And I said, Peter, why did you do this? And he said, I did the calculation for how many patients I can help in my entire professional career as an MD. And then I thought about how many patients I can affect if I make one good invention and bring it to market that's medically relevant. And that's actually my motivation, which is I went to medical school because I was interested in human biology. And that, in the end, was the reason for me completing all the medical school courses. And the science, in the beginning, I couldn't decide whether to go into pharmaceutical business, and I interviewed. And Hugo and I had the same experience, is that when you go to a pharmaceutical company, they show you the line chart. The line chart's the organizational chart of the company. So you're down here, and then there's the manager for your division and the manager for 5 divisions, and then there's the president of the company, and then there's the board of directors. And so my eyes always managed to move up. So I realized that in order for me to be successful in pharmaceutical business, I'd have to stop doing science and do management. And I wasn't interested in doing that. So I've never become a department chairman. I've never become a dean or a president, because I wanted to stay in my lab. And the motivation is also I've started several companies. In the Peter Johnson logic that I need to make sure that my science translates into real clinical activities. And so even now, I've started 2 clinical trials with MSCs as an investigator-initiated trial with a proper physician who's the PI, but I'm providing the technology behind the scenes. So the object is, and I think the advantage of your program is that it emphasizes translation. And I think the ability to actually see MSCs that I invented in several phase 3 clinical trials. Oh my goodness, what could be better? Because if one of those trials hits, it'll affect millions of people, more than I could ever do as a practicing physician. Not that being a practicing physician isn't a good thing. It's just that I can see the horizon where my scientific activities actually can have a huge impact. And I think that that's the motivation for people who are in medical school training. It could be dental school, could be nursing school. There's PhDs who are nurses. The object is how to take our civilization and get it to progress. Somebody asked me today whether I would be happy with the increase in life expectancy due to my inventions. And actually that has never been my motivation. The motivation is how to increase the number of years of healthy life. Not how long we live, but how healthy we can live. And that's why I can see, as a scientist, the activities that I now am pursuing are so much fun. I should have retired years ago, but you're going to have to drag me out of the laboratory because the things that we're doing now are so medically relevant and so translatable.
And so I wanted to follow up on that. Because through the years and encountering a large number of basic scientists in many different fields, it's not common to find someone who leads a clinical project. Most of the time, at least in my experience, when you interact with basic scientists, are somewhat fearful of pushing that area or trying to invade, if you will, in the clinician territory. But then you have the clinicians that don't understand the other part. So what made you develop that intellect or the spirit or the desire or the courage to advance clinical translational work, not as a scientist?
Well,
I think that's not a common.
No.
I mean, it's not something that you see in many people.
It's actually interesting because I never thought about that until this second. It was actually lucky that I chose to go to Case Western Reserve University. Mm-hmm. So I had 4 job offers, one at UCLA, one at Duke, one at Brandeis in Boston, and Case Western Reserve. And Case Western Reserve offered me an incredible package, a lab that was set up, a technician for many years, a budget. I mean, not such a great salary, but
I can understand that as an academic.
not such a great salary. And Cleveland didn't have such a great reputation like Boston or Los Angeles.
And back then, that was in the 70s?
This was 69. I came to Cleveland in September of 1960.
And Case Western was the Cleveland Clinic probably had
never existed. Cleveland
was irrelevant then.
Was more than irrelevant.
Yeah.
And so there were departments at the University Hospital associated with Case Western Reserve that were some of the departments, orthopedics in particular, that I was associated with. It probably wasn't number 1, but it was probably in the top 3 nationally. So Case Western Reserve Medical School in the 50s, before lots of you were born, right? So she sneered at that. In the 1950s, Case Western Reserve Medical School changed medical education worldwide. In all the medical schools, even Hopkins in the 60s was still doing this, you would take a course in biochemistry, a course in pathology, a course in microbiology, a course in neurohistology, etc. So you take all these separate courses. In the 1950s, Case Western Reserve faculty said, we're done with that, we're not doing that, we're going to study organ systems. So they would have a committee for cardiovascular. So that meant the biochemist, the cell biologist, the pathologist, the anatomist, the cardiologist, the anesthesiologist, all of the those departments had to come together as a committee and divide the lectures and decide what the students were going to hear about cardiovascular or musculoskeletal or neurobiology, etc. So there were these committees. So the school of medicine, and therefore the university, was interactive across departmental lines. So all these committee meetings meant that the faculty had to talk to one another. So this was a uniquely interactive community. And when I was an assistant professor, I got a telephone call. I'm in the biology department, so I dealt with all you young people. I do that on a daily basis. In the early 1970s, I got this call from some guy in orthopedics who said, I understand that you work on embryonic chick limb. Can you give grand rounds in orthopedics? Because we need some basic science for our residents. So I said, sure. So then I asked, when is it? 7 o'clock Saturday morning. Not so much fun for somebody who wasn't interested in giving a lecture at 7 in the morning. So I gave the lecture, and actually I prepared the lecture by going and finding out about human limb development. And that's where I ran across the fact that humans can regenerate fingertips if they're young enough and if it's manipulated properly, and you don't let the person go to the emergency room for the resident to put stitches through it because you'll get scar tissue. So I gave the lecture, and 3 weeks later, I got in the mail, in the old mail, I got a check for $300. That was like $1 million for me in those days. And so I called up the guy in orthopedics.
That was for the lecture?
That was for the lecture. Orthopedics, as we well know, is a very wealthy discipline, right? Mm-hmm. So I got a check for $300 for the lecture. So I called up the guy who invited me, and I said, anytime you need a lecture, call me. And that's how I started collaborating with a gentleman whose name was Victor Goldberg. Victor Goldberg eventually became the chairman of orthopedics, and for 30 years we collaborated. Clinician scientist, he had only an MD, not a PhD, and a PhD, and every Thursday morning at 6:30 before his first surgery, we would have a group meeting in his office. And so walking across the street to the hospital, or walking across the street to the medical school, or walking across the campus to the engineering school is what we do. And so this was lucky in a way that it allowed me very early in my career to focus my attention on real orthopedic problems, bone filling, etc. And from that, I'll talk to the oncologists tomorrow morning. And we invented an assay for MSCs and marrow by putting this in a porous calcium phosphate ceramic and putting it on the back of an animal and growing it as a separate habitat. This is how we study how melanoma gets into marrow. And so that old technique is now teaching us that the current dogma of how melanoma gets into bone, if melanoma gets into bone, you have 6 months to live. It's lethal. So how does it get into bone? The dogma is that the melanoma eats its way by secreting enzymes that dissolve away the bone, and it gets into the marrow. Completely wrong. The MSC pericyte that sits on the blood vessel reaches through the holes in the fenestrated blood vessels of marrow, puts SDF1 out into the bloodstream, attracts the melanoma, grabs the melanoma and pulls it into the marrow. So this MSC, which does all these wonderful therapeutic things,
Cancer is evil.
in cancer, it's the evil hand that grabs the melanoma and pulls it in, and we're studying the molecular mechanism of that activity to find molecules that will inhibit that. So here's this old assay that we created completely for orthopedic reasons, and I told one of the orthopods today who did tumor resection surgery, instead of putting a piece of allograft, which is dead wood, in this place, put a calcium phosphate ceramic, put marrow in that.
Repopulate with MSCs?
And repopulate with MSCs and make new bone and to load it in a particular way that the orthopedic guys understood, so that as the bone's being formed, the implant slowly being loaded so that the bone grows along the load lines. So this going to Case Western Reserve, random. Meeting Victor Goldberg, random. The atmosphere of walking across the street, standard operating procedure. At other places, University of Chicago, never. Never. Every department was a kingdom unto its own, as you understood. And the atmosphere of walking across the street, of walking across buildings, these are the bridges that Hugo's trying to build. So those bridges were already painted in the street. And so that was lucky for me because it allowed me the opportunity to have access to clinicians who are interested in basic research.
I think that the ability to do original translational research is unique to places that perhaps potentiate those two areas. Because it's not easy today. I mean, the regulatory aspects, the necessary drive from either one or the other requires really focus and good collaboration. And so since we're talking about now a little more research, and the complexities in the US are obviously perhaps not as big as the ones in here, but at the same time, the magnitude of the problems will be different because of the finances, but the ability to do this type of translational research in the US, do you think it will create a future that's hopeful for clinical development, or there has to be some other aspect, regulatory, funding, or a strategic development in the educational process that accelerate translational work? Because the fact of the matter is that it takes a very long time, pharmaceutical or cell-based therapies or simply a procedure that's new to come into the clinic. And what you want to comment on that, or how can we expedite in a safe manner the clinical translation of cell-based therapies?
Well, I can tell you what I'm doing. So you have to become politically active. You have to be politically active in your university and your medical school, and you have to think about how you set up policies and procedures. And then you have to be politically active with the regulatory agency, because the regulatory agencies have been trained by big pharma to be big pharma specific. So in cell-based therapy, we can't do 5,000 patient trial. For big pharma, so it's another $100 million, not a big deal. And so the regulators who are accused of being stupid, of course are not so stupid, they have to be educated. And we have to change the procedures. And there's only one group of people who can change the procedures, and that's the MD and the PhD. We have to lobby, we have to do this political lobbying to change procedures. So, for example, we got legislation passed by Congress that Obama signed, which is called the 21st Century Cures Act. And hidden in there is a whole section on how the FDA can change, is now given the legal right to change its methods of evaluating regenerative medicine therapies. The way it's written is that you don't need phase 3 trials. You need 5 to 10 years of post-marketing follow-up. So if a procedure is phase 3 ready, meaning the production of the cells, all of that is available, you could then not do a phase 3 trial, but you have to follow the patients for 10 years. Okay? But meanwhile, it's an approved procedure, it's approved drug, they get paid. And last Thursday, we got legislation, and when I say we, I helped write it. I went to Washington and talked to lobbyists. Friends went to congressmen and presented the language so that the congressmen's offices got the written language and they presented it as their bills in Congress. And so last Thursday, in the Senate, by a 94-1 vote, it passed this new legislation which gives the FDA the power to change its procedures and mandates a time frame, 18 months, that they have to do that.
That's interesting.
So how do we change our culture? We change it. We do it slowly, we do it professionally, and we make sure that always the patient is first and the health of the patient is protected. And second, that new procedures are given the opportunity, as long as they do no harm, to be tested.
So let me take the last few minutes to expand on how to implement clinical development with stem cells, or in whichever variation you may have them, or MSCs or cell-based therapies. Because of the simplicity in obtaining cell sources from the bone marrow or from fat tissue, there's been a number of major incidents, some in Mexico, some in the US and in the Caribbean, of places that provide patients with this great hope of regeneration. In fact, I had a patient that went to Singapore, was charged close to $100,000 to have a cell infusion that was going to cure his heart failure. Real story. I had another patient that went to Cancun. I don't know if any of you know, but there is a place in Cancun that people get cells, and they charge, these men pay $50,000 for it.
In Guadalajara.
Also.
Yeah.
But, and then there was a 60-minute program about a group in Monterrey that were treating patients with some form of, and I don't know exactly the cell type, but my commentary is more in this manner, is that because people look for hope, especially when they have illnesses that may be mortal. Right? They have the desire, like those that are believers, they pray a lot and they think you're going to get healed, and and then eventually there is a fine line between that and the magic and therapies. And those things are going on today. So how can we create a serious path? What do we need to do so that if we want to advance the field locally, do the right thing so that it's not perceived as commercial interests without real science?
So I'm currently lobbying for a website that every doctor must list the patient by number, anonymous, protect the identity of the patient, the clinical symptoms they're treating, the procedure that they use to treat them, and systematic outcome studies with time. So if the clinic in Cancun puts its outcome numbers, their participation of patients is going to go to, yeah, but that's the point. So if all of the honest physicians and all of the leading hospitals establish a transparent vehicle for patients to go to the website and see how Dr. X in Clinic Y is doing and what the outcomes, it's on the website. That's one. So if a doctor's not on the website, not going to go to his clinic. So the outcome reporting, that's number one. Number two, we have to change the way we consent patients. So cell-based therapy, if you go to the Mesoblast website for low back pain, you put in 6 million MSCs and your back pain goes away. 2-year outcomes. 50 to 60% non-responders. Not that it doesn't work. It's just that those patients don't respond. And there's an opportunity actually to increase the response rate. That's a different story. So now in the clinic, if I give someone that shot, I should consent them by saying, you have less than a 50-50 chance that this is going to work. But I think this is better than a spinal fusion, and you should try this. So because I've seen it work, but also it's 50-50 chance.
How were these cell-based therapies approved in the U.S.?
None are approved. All at the moment are in phase 3 clinical trials.
Okay.
And so acute myocardial infarct, chronic heart failure, diabetes, low back pain, graft versus host disease, all of these are in phase 3 clinical trials.
But the orthopedics, they use a lot of
right. So
of label, or there is some.
No, that's not off label.
Not off label, or
no? They're first of all, in the United States, over 700 private clinics advertise on the web for cell-based therapies for stem cells. Right. So when I lectured, the first thing I said is I begged the audience, I don't beg easily. I begged the audience not to call MSC stem cells because they're not stem cells in the body. And that's the problem with consenting. So the idea is if I put MSCs in your knee, what you have in your head is this stem cell procedure. Those stem cells are going to go in, become chondrocytes, and make new cartilage. Not what happens.
Of course.
So, yeah, but that's the bad thing that I did. I called them stem cells. They're not stem cells. They're drug factories for sites of damage. And we now know how they work, and we now know some of the molecules that are doing these good things, including in the knee. The MSCs make molecules, proteins, that sit on opioid receptors. So within 3 to 4 days, the pain goes away with no change in the clinical profile. But the pain goes away. All of the people who come to the orthopedic group come because of pain. And what happens is that they come and they say, "Doctor, my right knee is killing me. Its pain is so hard." So you roll up his pants leg and you see that the knee is swollen. You roll up the other leg, pants leg, and that knee's also swollen, but it doesn't hurt him. So the clinical outcomes are pain measurements, not how bad the cartilage is on MRI. So we also have to change the education of the patient to be more sensitive to the fact that one knee's bone on bone and one knee has a chance that some of the cartilage can regenerate itself. So again, it's a question of verbiage, how we communicate with the patient, and what the expectation is. It's okay to tell the patient that this drug works in 30% of the patients. So it's going to cost you $2,000 out of your pocket because the insurance doesn't cover it. Is that okay? But I think it's better than a metal knee. And so the patient then becomes involved in the decision process. Whatever you say as a doctor, the patients will accept. Whatever you say, however crazy the idea is, if you say, "I know you're here because you're trying to buy hope. I don't have any hope for sale. I have this procedure, which in a low frequency of cases really works because we have this data that's published." But that's the way we also have to consent the patient, by being A, transparent, putting our names on the website, and number two, by telling the patient this has a 30% or a 50% chance of working. And I think that by you as being president, raising the bar in your faculty, making every faculty member on your website at the hospital put outcome measures.
Yes, that's very good.
By
like
putting
that.
out,
We are trying to do that.
yeah, but that's
Not
exactly
individually yet.
exactly by an individual basis and by a department basis, which some of the doctors won't like. I guarantee, I give you a money back written guarantee. But in the end, your hospital will become famous because your outcome numbers are transparent. Not that your outcome numbers are 100%, but
It creates confidence. People will trust you.
it creates trust. And that's the most important commodity that is being misused by the private clinics. There's some people, I know a lab in Panama. I know a lab in Florida. I know a lab in New York City that does MSC therapy, completely illegal by US standards. But if somebody has MS and there's a 50% chance that an infusion intrathecally of MSCs can stop the disease, why not?
So did you talk about is Hector Ramon here or no? Is Hector? So you're aware of his work with
Yeah, of
ALS.
course. Of course. So
But
I was both educated and educated the audience.
But see, the issue is, how do you fund work like that here?
There's only
Or anywhere,
well,
for that
I-
matter,
I-
in a responsible manner.
I think the way you fund this is there's so I
Is it okay to bill the patient when we don't have proof?
I think if you want 5,000 patients who've been in a clinical trial as proof.
No, I understand that's not going to happen.
Yeah, but
Now.
again, but again, if you do 10 patients and you don't see a positive outcome, you're done with that. That's called a phase 1 trial. It's
Okay.
safe, and B, you have outcome parameters. If it don't make the outcome parameters with 10 patients, it's not going to make it with 100 or 1,000. And so this transparency becomes obligatory, so that when in our, we have a clinical trial that I started with cystic fibrosis kids, have horrible lung infections. We give them allogeneic MSCs, which make molecules that kill bacteria.
Intranasally or?
Absolutely not. You can only put it in their veins.
Okay.
So if I could convince the FDA, I would do it retroorbitally, because if you put there's so much blood vessels behind your eye, they automatically dump in your lung. That's where I want them. But you have to do it intravenously. That's the only thing the FDA would approve, especially with kids.
Okay. How do you support it? How do you fund it?
So the national,
A grant?
no. There's a Society for Cystic Fibrosis.
Okay.
There's an agency. So it's partially funded by them. And then I found a benefactor. No, the benefactor pays for all the basic science. The Cystic Fibrosis Foundation pays for the health care. So we have a phase 1 trial, and what I told the benefactor is, if we can't get outside funding from an agency or from the NIH, I don't want your money, because it validates the logic of the grant. But I think we're academics, you and I. We're professional beggars. We've been trained to beg for money. That's how we exist. And so I'm happy to be a beggar, because in the end result, we'll do cutting-edge clinical trials that couldn't be done by simple review of national agencies. And so it's okay. Remember, I started out as a very poor boy, so being a beggar is not a big deal for me.
So let me ask you a final question, since we're coming now to the end. Among all the different applications that you have seen and that you've worked, or others have worked with your ideas, what would you think will be the major, or the closest to a major significant clinical change in practice? Perhaps other than the orthopedic applications.
I think my contribution to medical care will be the use of cell-based therapy, because every invention, no matter what the invention is, from the first time it's made public till the time it comes to market, it's 20 years. There's no exception to that rule that I know. Your fancy phone, you think is the newest, hottest thing that was invented. In World War II, they called them walkie-talkies. Same concept, you just have smaller components. And so cell-based therapy, which did not exist 25 years ago when we started working on it, now exists. So the opportunity, if you go to clinicaltrials.gov, 750 clinical trials using MSCs are listed. Even if 10 of those are successful, I'm happy. So again, I think what we know about MSCs is that MSCs manage the innate regenerative capabilities of the patient. That's what doctors are supposed to do. So I gave them another very powerful tool to be used in a variety of clinical circumstances, and that for me is hugely important. There's one last comment that I want to make to all the young people. So on my tombstone, it won't say great scientist, wonderful clinician. It'll say husband, father, grandfather. So family and your honor are what you carry with you all your life. And so my most impressive achievement is that I just spent all of last week with my 2 grown children and my 6 grandchildren and their spouses, and we stayed in one house for 1 week, and we cooked all of our meals together, and we still are friends.
Well, I think that will be a very good closing statement, and I think that, well, I think, you leave us with perhaps what's important in life, and I think that I'll make my summary of your presentation, which is the excitement of science, which is different than the excitement of taking of an individual. That's very powerful. But the excitement of science, when you really learn it and appreciate it, it's equal or even more powerful because of the magnitude of the benefit that you can have. But I suppose at the end of the day, that's all part of being a good person and accomplish your mission. And I guess we at Monterrey Tech at the university, we have a sister university. And our sister university is called Tech Millennium. And the purpose of that university, just like in our university, we are trying to create leaders and people that are successful in their careers and change the world. Our sister university has a different purpose. And that purpose is to make people aware that they have a purpose in life. And I guess what you are discussing here, or the time that we spend, we are learning how to combine maybe these 2 fields to really be very, to develop that love for science and be very successful. But at the same time, carry that principle of family honor, and which makes a happy life, I guess, at the end. I just had a daughter that got married, so I guess I empathize with the issue of family and honor, and I think I appreciate your comments very much.
There's nothing better than dancing with the new bride who's your daughter.
Not easy. I cry a lot. I couldn't stop crying walking in the church. But anyway, Dr. Caplan, I think we may have time if somebody, maybe I'll ask Hugo if you want to make a comment, and we close. It's a little after 8 o'clock, and I think I just want to make sure that everybody appreciate the importance of this conversation, and I hope that for those of you that are younger than many of us here, understand the beauty of science, which is different. I mean, I think many of us, most of the people here are physicians, or physicians in preparation. And not everybody appreciates the love of science, but I think that seeing someone whose entire career has been dedicated to that, it should provide you as an example. And then I encourage you also to get in contact with many of us that are doing research so that you can get first-hand experience of the beauty of that and the importance of using science as a way to learn to open your mind and then pursue better solutions to problems in life, not only in science, because I think it helps you everywhere. Hugo, do you want to make a comment?
A brief one. Besides what you have summarized of the lessons that Dr. Caplan is giving today to us, I was struck what you say, that by having bridges between the medical school and the clinics allows you to work in real world problems. So what we are trying to do here, and I see very bright future for this institution, is to put together the basic scientists and the clinical scientists. So the basic scientists understand the real world problems, and the clinical scientists understand the power of science. And together they can really make a difference. Thank you very much.
Muchas gracias. Dr. Caplan, thank you. So Manuel is going to give you a little present.
Gift. A small gift. This is our mascot. If you don't want it in your desk, maybe for one of your grandchildren, it could be very good.
No, they'll fight over it. Thank you.
Thank you very much for being with us. Very inspiring talk for our students, and welcome every time to Monterrey, Tech of Monterrey.
Okay.